All right, should we start?
Yes.
Okay, then. Well, good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor David Kofke. Professor Kofke holds a bachelor's from Carnegie Mellon University and a PhD degree in chemical engineering from the University of Pennsylvania. Currently, he's a Sunny Distinguished Professor at the State University of New York, the University at Buffalo, and is the Director of Undergraduate Studies in the Chemical and Biological Engineering Department. His research focuses on statistical physics, molecular modeling and simulation, and software engineering. His group is focused on the development of molecular simulation methods, particularly as they pertain to free energy calculations and configurational integrals. He currently has activities examining the development and application of very efficient map averaging methods and synthesis of integral equation methods and molecular simulation for the purpose of calculating virial coefficients and other properties more efficiently. Professor Kofke is author of over 140 refereed publications, and he has been an associate editor of Journal of Chemical Engineering Data since 2016. So once again, welcome, Professor David Kofke. Thank you so much for being here with us, and please feel free to start your presentation.
Well, thank you for that kind introduction. Let me get my screen shared here. Okay, and then let me presentation mode. So everyone, I hope can see that. So it's great to be here. It's clearly a long line of distinguished speakers who have participated in this seminar series. It's really been very interesting to see the ones that I've seen, and I'm hoping that I can make a contribution to that as well. So let me start. I'm going to be talking about bridging molecular modeling and thermodynamic properties, and the approach that I'm particularly interested in are methods that are based on what we call, or what are called, cluster integrals. So here's a brief outline of my talk. I'll be talking generally about the ways to go from molecular models to thermodynamics. I'll then spend a bit of time talking about how virial coefficients are computed. So those are the sort of the most widely known of the cluster integrals that are used. I'll then go through a variety of applications. And then if time permits, I will talk a bit about convergence, which I think is a particularly interesting topic. So this is the general picture of sort of the holy grail of what we would like to be able to do as people who do molecular thermodynamics. We would like to be able, in principle, to start from quantum mechanics, which is represented over here, and then solve the Schrodinger equation or some equivalent representation of it to be able to compute configurational energies. And then we know from statistical mechanics how we can do ensemble averages or molecular dynamics calculations in order to bridge the gap from the molecules to the thermodynamic properties, which we are generally interested in. And then, if you're into chemical engineering or other types of applications, you might use those for actual practical purposes. So the methods for doing this have advanced quite a bit, particularly in the past couple of decades. And we believe that molecular modeling is really reaching a mainstream capabilities for providing physical property data. And I think a strong recognition of this is the Journal of Chemical and Engineering Data, which has a long history of providing high quality data from experimental sources. In 2016, started encouraging the submission of papers that contain data and that present data that are obtained from molecular modeling. So this is further represented by the fact that, I'm an associate editor, one of the associate editors for the journal, and I do molecular modeling primarily. And Ilya Seitman has somewhat recently been appointed as editor-in-chief of the journal, and he is a molecular modeler for sure. And he was one of the speakers in this series previously. So I think this shows that molecular modeling is really coming of age as a tool for doing quantitative practical calculations for properties. So going back to this picture, So we realize, of course, we don't go from directly from quantum mechanics to the intermolecular or configurational energies. We have a bridge that helps us, get across this gap. And this bridge traditionally has been in the form of force fields, which are formulas that describe the energy or the various contributions to the energy as we understand them from various types of interactions and motions and intramolecular motions of the molecules. So these approaches are not rigorous. They aren't an exact representation or an exact bridge from the the quantum mechanics to the configurational energies. They can be informed from quantum mechanical calculations, but they also take a lot of their input from experimental data. And that's what I'm trying to represent by this arrow that's sort of going back. So they are at least semi-empirical typically in their calculations, although people are trying to develop molecular models that are informed more and more primarily from quantum mechanics. There are emerging, I think, an exciting new set of approaches for bridging this gap, and these are methods based on machine learning. And these approaches, I think we've all heard about them, but they are attempting to take a rich set of data from quantum mechanics for intermolecular energies, for pairs and triples and various numbers of molecules, and basically fitting them in a very sophisticated way using these techniques that have given us the ability to recognize pictures and all the other things that we know machine learning is doing. So these have been, an important advance, and I think there's a lot of potential for the more developments in this direction in the future. So the other side of this, of course, is a big part of it as well. And the general method for bridging this gap has been molecular simulation. And at least for trying to develop a rigorous way. And that's really one of the appealing features of molecular simulation is if you input a molecular model or even a machine learning model for the configurational energies and run that through a molecular simulation, you will get a rigorous, exact representation of the properties. And this contrasts with the long used approach for trying to develop means for predicting properties, which are based on what you might call engineering or molecular thermodynamic models, which have some degree of approximation in them, although they are, of course, very powerful and very useful. But they don't have the same rigor that molecular simulation will give you. So the thrust of this talk, though, is to point out that molecular simulation is not the only way of giving us a rigorous bridge from the molecular scale to the thermodynamic scale. And the idea here is that cluster integrals are another approach that allows us to bridge this gap. And these have certain advantages and disadvantages that I would like to spend most of this talk discussing. So what are cluster integrals? Well, they go back to the work of Mayer and Mayer in the 40s. And the most widely known approach for cluster integrals or the application of cluster integrals is through the Virial equation of state. And that's what I'll be focusing on pretty much exclusively in this talk. So the Virial equation of state is a formula that gives you the pressure as a function of density, which is given by rho here, and the temperature. And the coefficients in this equation of state, which is written as a series expansion in the density, are the Virial coefficients. And these are dependent only on temperature. They can also depend on mole fraction or composition if you have a mixture. But we'll focus for the moment on pure substances, but we'll be talking a little bit later about mixtures. So the way these coefficients are evaluated and their connection to the molecular scale is given through this example, which I give the formula for the fourth virial coefficient, B4. And this is for a pairwise additive molecular model. And it's just given as an integral in which you move molecules 2, 3, and 4 around, keeping molecule 1 fixed to define an origin. And the thing that we are integrating in this are these products of so-called Mayer functions. And you'll see that these functional forms of these products are represented most conveniently in terms of these graphs. So the graph with, is written as a square here, you can see if you label the points for the purpose of identifying them, you would have a bond between 1 and 2. That's the F1,2 bond. You have an F2,3 bond, an F3,4 bond, and an F1,4 bond. So that's this term. And then we take the same thing and add a 1,3 bond, and we get, a line here. And then we take that and also add an F2,4 bond, and we get that. So again, it's not easy to derive, but this is the correct exact formula, at least for pairwise potentials, for the fourth virial coefficient, which appears in this equation of state. So I'll be representing these later on with more of these graphs. So I just want to make sure you understand what these graphs represent. They're these products of Mayer functions. So the Mayer function is written for a simple spherical potential in the form shown here. It's given as a Boltzmann factor of the potential, -1. There's your temperature dependence in beta, that's 1 over kT. And the Mayer function looks like this. Qualitatively, it goes to 0 at large separations, and it's negative for overlapping configurations. And this is the way that it's done then. This is the bridge or the route for going from quantum mechanics, represented over here, through the intermolecular potential, however you get that. And then from there, you can get the virial coefficient, which goes into here, which then gives you the thermodynamic properties. I should add, I talked about virial coefficients, but there's other types of cluster integrals. If you want dielectric constants or interfacial properties or other things, there's other types of cluster integrals that can be defined for those properties as well. So why would we be interested in doing this? Well, it's really a completely unique approach to making this bridge from molecular to thermodynamics. It's got a lot of things in common with simulation. It does give you, again, a rigorous bridge. It's an exact thermodynamic description for the given molecular model. It's got the theoretically correct dependence on all of the state variables, particularly the mole fraction. So if you're interested in mixtures, you've got the exact form for the dependence on mole fractions. It really can accommodate any level of complexity. You can, again, I said you can do mixtures. If you have flexibility, there's ways of handling that. You've got multi-body potentials. I talked about pairwise, but multi-body is easily handled. You can do inhomogeneous systems. You can handle nuclear quantum effects and all of these things. And it really can give you a broad range of thermodynamic properties. When I say thermodynamic, I mean equilibrium thermodynamics. It doesn't give you transport properties. There's other approaches for doing that, but that's not something that I've been working on. Similar to a thermodynamic model, and unlike simulation, it gives you an equation. It gives you that rather than a discrete set of data. The coefficients that you compute, they're reusable and transferable to other types of mixtures and so on, and it's useful for many practical applications, just like a thermodynamic model. And unique to cluster methods is that although it starts from a molecular model, it does describe the thermodynamic limit. And this is, again, something that's not quite obvious, but unlike simulation, the data that you get, the results that you get, the properties that you get are the values in the thermodynamic limit, as long as the series is converged. It is applicable only to non-condensed phases, and that's obviously not a feature. It's an unfortunate fact about the model is that you can't apply it to liquids as far as we know now. And it also has limits to convergence. So if you go to very high densities, whatever that means, is going to fail. But on the other hand, the failure is detectable. And if the model is not describing or not making an appropriate bridge, you can detect it by looking at different orders in the series. And it's systematically improvable in that sense. And that's a really nice feature to have in any type of a model you're working on. It can be interfaced to try to overcome these limits with other known behavior to form approximants. I think Richard Elliott spoke a while back about some virial coefficient work and gave a very interesting talk. And he refers to this, I believe, as renormalization. So if I have time at the end of my talk, I'll be discussing that a bit. It does have links with thermodynamic perturbation theory to develop temperature and density series. And again, Richard Elliott talked about that. And frankly, we're still trying to understand how it works, although it's been around for quite a while. So let me talk a little bit about how these configurational integrals or virial coefficients are computed. So we've got our general configurational integral as shown here. This is for the nth arbitrary virial coefficient. We've got some integrand here, and you saw it for B4. It's a sum of 3 terms, but in general, you've got a bunch of terms there. So the first thing you have to do is generate configurations of the molecules that you are doing this calculation. So it's like a simulation or a molecular simulation in that sense. So we developed a method a number of years back that we call Mayer sampling Monte Carlo. It's importance sampling based on this integrand. It's made a little bit complicated because the integrand can be negative as well as positive. So we have to take some measures to handle that. That's the first bit that I'll be talking about. We also, I just reviewed this. This was a paper where we introduced this with graduate student Jayon Singh. And the idea is we, been working in free energies for a while. Those are configurational integrals. And we realized that, these ideas that are used for free energies can be applied to the calculation of these cluster integrals. So we have to figure out what average we need to evaluate. And we have a method that I like to call overlap sampling. It's a form of what's more broadly known as Bennis method or M-bar, but applied to this. It's a little tricky again, because you have the negative integrand, but it's pretty straightforward to do. I won't give any details about that. The other thing you have to deal with is the evaluation. Oops, I do have a little simulation here to remind us, to show you what this looks like. So everyone likes a little animation. So this is actually a Mayer sampling Monte Carlo simulation. We're computing the 4th virial coefficient of water. And so this is showing you, as I started this, these are the configurations that are going to be sampled. So we've just started doing that. So we're sampling, we're doing the importance sampling or the Mayer sampling in this calculation. And we've got 2 systems that we're simulating here. And this is the element of the so-called overlap sampling. You're simulating a target system, the one that you want to get the virial coefficient for. And you're also simulating a reference system, which in this case is hard spheres. So you'll see that these configurations are somewhat unlike what you would expect to see in a traditional molecular simulation. The molecules overlap each other, and perhaps most interestingly, there's no volume. You don't define a finite volume that you put these in. The importance sampling keeps them together because the integrand goes to 0 as any of them get far away from any of the others. So you collect averages for these, and as it proceeds, you can see this is a system of hard spheres. So these will actually never not be overlapping, although they're drawn as water molecules in this simulation, this half of the simulation, they're actually working as hard spheres. Anyway, so that gives you a flavor of what the calculations or how the calculations work. The other aspect of this is you need to evaluate that integrand, this FB, for each configuration that you just saw generated here. And in principle, this is straightforward. You evaluate these graphs. The graphs are defined as all of the graphs that you can write that are called doubly connected. They have no articulation points. There's no single point that you can remove and break it into 2 pieces, and they're also connected. So how many graphs do we have to sum? Well, this gives you a feel for it. This is all of the graphs that you could have for 2 points. So you've got the connected graph and you've got the disconnected graph. So there's 2 of them, and half of them are biconnected. One of the 2 is contributing. So as you go to B3, well, in principle, you as many as 8 graphs, but all of these are singly connected or not biconnected. The only one that contributes is this one. So 13% of them contribute there. As you go to B4, I can't draw them all here, but there's 64 of them. They go as, in this form, 2 to the n times n minus 1 over 2. That's the value that's shown here. And again, 16 of these, I believe, or no, 8 of these are biconnected. So that's 16%. As you go to B5, there's 1,000 of them, where 23% of them are biconnected. 6, there's 32,000, whereas about 1/3 of them are biconnected that you have to add up. As you get up to 8, there's, what's that, 200 million, almost 300 million, and 2/3 of them are relevant, so you would have to add those up. As you get up to 10, it's this many. I don't know how many billions or quintillions we have here, but 83% of them. So you can see a larger number of them become biconnected, and obviously it's really exploding in terms of the number of graphs that you need to deal with. So if you were to try to do B12, you would have to sum basically 93% of this number of graphs for each configuration that you generate. And finally, I like to point out, when you get to 13, you've got half a mole of graphs, 96% of which are biconnected, and you would have to add up. So clearly, that's not going to happen. You're going to add 10 to the 23rd graphs and expect to finish in any reasonable time. So this was broken through, though, by Richard Wheatley, who came up with an extremely clever algorithm in 2013. And the algorithm generally goes as shown here. He basically starts with the sum of all of the diagrams. All of those 10 to the 23rd diagrams can be evaluated in one go, believe it or not, just by evaluating this single diagram where you replace each bond with that bond plus one. And if you work out all the products, you see that all of these are basically contained in that. And then you go about systematically removing the parts that you don't want, which are all the non-bi-connected diagrams. And he has a nice recursive algorithm for doing that. He first removes the disconnected algorithms. That leaves just the connected ones. And then he subtracts the articulated ones, again, through this recursive approach. And that leaves you with what you want, or just the bi-connected diagrams. So this recursive scheme that he came up with makes this extremely efficient. The CPU increases still exponentially, but it's only 3 to the n as opposed to 2 to the n squared. Later, very nice work, again, a beautiful derivation by Richard, showed that this was applicable not only for pairwise potentials, but for non-pairwise. So we can apply this to realistic models where non-pairwise interactions really are relevant if you want to get quantitative property calculations. So it also turns out to be very easy to extend this calculation to compute derivatives of these cluster integrals. And those are needed, for example, the temperature derivatives are needed for the heat capacity and thermal expansion coefficient and other things, as I'll show in a moment. So just to give you an idea of how much you save by going from 3 to the n, from this rate of increase to 3 to the n, this gives you basically 3 to the n. You can see by the time you get to 13, instead of having half a mole, you've got roughly 1 million diagrams that you're trying to sum, or 1 million operations, or time-wise that this takes. Okay, so so with that in place, we were able to really break through. There's still limits. We can't do B100 by any means, but we do have some heroic calculations. We sort of did this to see how far we could take it. So hard spheres have been computed up to B12. We computed the B16, believe it or not, for the Leonard-Jones model at 1 temperature. Lower temperature turns out to be easier to get good results in higher temperatures, so we just did that there. Temperature dependent square well model, we've gotten values for the coefficients there up to B9, and square well has a nice analytic temperature dependence, so you just have to break that into parts. So for simple models, it's feasible to get B7 or maybe B8 without unusual effort. Again, depends on your quality of your computers and how much time you're really willing to invest in it, but these are not out of reach, I think, for typical calculation. Things that will limit your ability to compute to higher order, of course, will be a more computationally expensive molecular model. So of course, hard spheres or Leonard-Jones are as easy as it gets. If you have intramolecular flexibility, there's actually other terms that you have to add to the coefficients to account for that effect. And those do complicate things quite a bit, and we don't have a really great handle on that. We know how to do it, but we don't have super efficient methods for getting that like we do for the other cases. Nuclear quantum effects can be relevant, and again, those can be handled with semi-classical or path integral methods, both of which are going to add a bit more complication to the calculation. So I'd like to go on and talk a bit about some applications. So this was a study we did a while back looking at carbon dioxide and methane mixtures. And we chose this because there was a really nice paper by this group, Charles Abro and Ed McGinn and Cassiona Amoli. And they did molecular simulation calculations for this mixture. And it was very, very thorough. And it was in the region of states that the virial equation state can be applied. So they reported 7 properties at 4 supercritical temperatures. They did 11 compositions from the pure, one component to the other pure component and 14 pressures. So it was a very comprehensive set of data. And the nice thing about this is we can take the same molecular model and try to compute properties as well. So we did this. We went up to 7th order for each of the 4 temperatures, and we computed all of the mixture coefficients that are needed to get up to there. These are the various mixture coefficients. So here's a Mayer sampling calculation for this looks like maybe B7. Yes, there's 4 CO2, 4 methanes and 3 CO2s. We also, we didn't have our methods for computing derivatives at this time, so we had to compute these by fitting to the 4 temperatures, and that is not really the best way to do it, but it's what we had. So here are some of the results. So this is showing the virial coefficient, scaled by a density that puts them all sort of on the same scale. And this is showing the various mixtures. So there's 3 coefficients for B2, there's 4 for B3, and 5 for B4, and so on. And this is for one particular temperature, again, for pure CH4 to pure CO2. And I'll just point out that there, if you compare this is based, I should say, on the trap model, which is what the molecular simulations used. And you can note that there is a deviation, and it's sort of compensating deviations. B2 is sort of underestimated compared to experiment, which is what's given by this other point. And B3 is, B2 was overestimated, B3 was underestimated compared to experiment. So you sort of have this cancellation of errors, and this is not a huge surprise. The trap model is relatively simple model, and it's fit to experimental data, and it's not meant to describe the exact interactions, but it's supposed to do it well enough to give you good properties. So this is sort of a characteristic of the compromise that it makes. It doesn't get these coefficients exactly right, but it does it in a way that sort of compensates the errors. So I'll present a bunch of plots now that show results for the compressibility factor. In this case, the pressure is a function of density. Right now, I have this for one temperature, one composition. And you can see the various orders of the virial equation of state that are shown by the different colored lines, culminating with V7, or VOS7 as we call it, which agrees quite nicely with the molecular simulation data for the same model that was reported in the earlier paper. So I put a star on that diagram to help you identify the ones that are going to be showing up. So this just shows you what happens as you vary the temperature. Again, at the same composition, it's a mole fraction of 0.6 of CO2, I believe. And you can see you get very good agreement, particularly when you get up to 7th order, except down here where we get to the lowest temperature. I'll talk about that more in a moment, but you can see the virial equation is not agreeing super well with the simulations. And then as we go in varying mole fraction, as we go up and down, here's again our sort of home diagram. You can see that for this temperature, we have rather poor agreement for pure CO2, but it doesn't do so bad for pure methane. Okay, and then this is the whole grid of sort of compositions going up and down and temperatures going left and right. And, as you move down in this direction, we're getting very good agreement. As we move up in here, you can see it's not working so well. And the reason this doesn't work so well is because we are close to the critical point up here. The critical point of CO2, I'm not sure what it is for this model. It's about 300 and some Kelvin. And this is pure CO2 over here. So, this shows you one of the ways in which the virial equation of state can fail. It's an analytic equation. We know the critical point has difficulties being captured analytically, and we have approaches that we're trying to take to get around that. But this is sort of the direct thing that happens whenever you do these calculations, these applications. So this is, another property. There's a variety of properties we can look at. The Joule-Thomson coefficient is particularly challenging to get well. You can see the molecular simulations in particular have trouble getting it with high precision, whereas the virial equation of state does a good job of matching the simulations and has much greater precision as well. Again, breaking down up here. But this is a very rigorous test of an equation of state, is to look at how well it describes the Joule-Thomson coefficient. You can see the Virial equation, at least up to 7th order, does a pretty good job over a lot of the state space here. This is a graph that tries to get across the computational effort that is needed to get properties by simulation and comparing it to the Virial equation of state. And the colors here are representing the CPU time that's needed to get the property with 1% precision. So it goes from a millisecond, which is white, up to a CPU century, which is given in black. And again, so I've got 3 properties here: the compressibility factor, the Joule-Thomson coefficient, and the coefficient of thermal expansion. The points are what were given from the molecular simulation. Again, the paper not only gave properties, but they gave CPU times. It's a very difficult thing to compare apples to apples, because we're comparing the effort it takes to get 1 point with the effort it takes to get this whole set of conditions that's given by the Virial equation of state. But it does get a bit of the idea across. And you can see that, you certainly would rather be in the white or the blue compared to the red. So in a condition here, you can see that, doing the Virial equation of state is really much, much more efficient way of getting the properties compared to molecular simulation. Where the Virial equation has difficulty converging, or where you're going through the zero, the percentage, becomes difficult to get small, of course, if the thing you're normalizing with respect to is going through 0. So that's what's happening in here. So again, it gives you a sense of why you might prefer to do the Virial equation of state over simulation, just from the standpoint of efficiency. Okay, so that was again the Leonard-Jones model, or a simple empirical model or semi-empirical model for properties. I'd like to move on now to helium and calculations that are based on ab initio data. So we have 2 papers that we published in JCED. One is computing the Virial coefficients for the equation of state, the pressure, and the other is speed of sound. So I'll be talking about that here. Why are we interested in helium? Well, it's a good starting point, of course, for any type of difficult thing that you want to do, but it's also as practical applications. The people at NIST were very interested in trying to get a really good model for helium, because it's important for metrology applications that they do. So that's what motivated us to move in this direction. There's also, helium, of course, is just a single spherical atom. And so there are very good, high quality 2- and 3-body potentials that have been published for this. And these continue to be refined, but this just summarizes the ab initio calculations that were fit and published by these groups over the past couple of, 10 years or so. And they provide an estimate of the accuracy of their calculations as well. So this gives sort of a history of the calculation of Virial coefficients for helium based on ab initio calculations. Goes back to 2000. This just lists the order of the coefficient that was computed. We did up to 7th order in our calculations, which molecular model, the various methods based on just solution of the Schrodinger equation, or path integrals, or semi-classical methods, some classical calculations that we did. The temperature range in which it's looked at, whether people try to quantify the systematic error, which is important for gauging, how good your results are, of course. Helium is interesting also because helium-3, helium-4 isotopes have qualitatively different behavior. Some of these also gave acoustic derivatives, which is one of the things we looked at with temperature derivatives, and others did transport properties. So it's been well studied. So this summarizes sort of the performance that we're able to get compared to experiment. So what I'm plotting here are the various errors in the compressibility factor as a function of pressure going up to rather high pressures. And this is at one specific temperature, rather low temperature. And what I'm showing here with the numerals is this is the contribution to Z from that coefficient. So if you were to neglect this coefficient, you would have an error that's of this order. So this is what you get when you add in B3. This is how much B4 contributes. This is B5, how much B6. You can see it's clearly converging. As we add more terms, they're contributing less and less. So you can get an idea of how much error you have by convergence by looking at this. You can see that, if we include B7, well, truncation of the series is not the limiting error anymore. Okay, and that's over the whole range of conditions. The other thing we have here are the systematic error. This is based on the systematic errors in the potentials that were published with them. And we try to propagate that to the coefficients and how much that contributes to the error in Z. So that's really the limiting error that we have. And then we have stochastic error in our coefficients because they're computed via Monte Carlo, and that's given by way down here, and that's not significant. So the experimentalists who presented data for them of course, did a very good, thorough job, and they tried to quantify their error as well. Experiments are not absolutely perfect. They have sources of error too, and good experimentalists will try to quantify that. So we're able to present that here as well. And you can see that they have stochastic error. If they reproduce it, do the experiment over, how much does it change? And that's given by these squares here. And they also estimate systematic errors due to compressibility of a sinker that they use to do the measurements and other things where they try to estimate the errors in their, in these features. So you can see that you want to compare sort of the largest error in the experiments to the largest error in the equation of state. And you can see that we are, below the experimental error over all of these conditions. So, this is a way allows us to cautiously assert that we're able to measure, or I should say compute, the properties over these conditions, more precisely and more accurately than they can be measured experimentally. So this is the type of thing we would like to be able to do more broadly for other types of materials. The other thing we looked at was the speed of sound. So these are, again, computable from the Virial equation of state. You need the temperature derivatives. It's given in terms of the heat capacities, the compressibility. The heat capacity is given in terms of these terms, and these all are based on the Virial coefficients and their derivatives, which are given by the primes. So we can compute this as well, and property is interesting because it's a great way to measure properties experimentally. Everything is sort of a mechanical quantity that you're using to do the measurement. So it's preferred by experimentalists for certain types of equation of state measurements. Anyway, so these are our data that were published by Gammon in '76, and this is just showing the speed of sound versus pressure along this axis for a whole bunch of different temperatures. So that's what the data look like. If we take this and subtract the values given by the Virial equation, you can see that this should be 0. And to the extent that it's not 0, we can attribute that to inaccuracies in the estimates of the temperatures that the experimentalists estimated for it or reported for it. So we can use the Virial equation of state to correct the temperatures then for these. And from that, we can generate plots like this that allow us to do an estimate of the Virial coefficient, say omega k. We do the same term here, but we omit one of the terms in this sum, and we get a plot like this. And then by fitting this, we can get an estimate for this term. So you can see, we have a good description over a lot of these conditions, but in some places we still don't have a great characterization, and that could be due to errors in the experiments or in the simulations. So anyway, from that, we can get results like this that allow us to compute the difference in the third acoustic Virial coefficient relative to experiment. You can see that those are plotted by the points here with error bars. That's plotted on the left. On the right, we're plotting the difference divided by the uncertainty. So to the extent that this is less than 1, we can sort of have confidence that we are in agreement with the experiment. On the other hand, there seems to be a systematic deviation. All the points seem to be below in both of these. So there is some systematic deviation, but it's at least within the uncertainties of the calculations and the experiments. So there have been other first principle calculations, which are summarized here. You can see the various types of molecules that have been looked at. There's two that I want to call out in particular. Robert Hellman has done some really nice work doing ab initio surfaces and computing virial coefficients from it. He's gone up to the 8th virial coefficient for CO2 based on an ab initio potential. And then just last week, I saw this paper, I think maybe even this week, by Graham and Wheatley, that came out where they went further and looked at CO2 argon mixtures going up to the 5th virial coefficient. So I'd just like to present some of their results here. This is showing the Joule-Thomson coefficient. This is for pure CO2. So this is based on Hellman's virial coefficients. And we also have values based on the trap model. We only have trap values up to 1000 Kelvin. So the lines end here. But you can see that the various orders of the equation of state going from 3rd to 4th to 5th, you can see there's a convergence and it's going through this peak. And that seems to be in pretty decent agreement with the experiment, which are rather old data. This is really a very difficult thing to measure experimentally, the inversion point, the Joule-Thomson inversion. And over here, just to give a scale, this is the coexistence line ending with the critical point. So you can see the critical point obviously is right around here. And as I said before, the virial equation state isn't going to describe behavior there that well. But you can see it's doing a pretty good job, again, all from first principles calculations. So again, Graham and Wheatley, again, in this paper that just came out, they looked at CO2 argon mixtures. They went up to B5. Again, they did first principles ab initio for 2 and 3 body interactions, as did Hellman. Interestingly, they used a machine learning method for interpolation. And again, I think this could be the wave of the future for these types of calculations. So, Graham and Wheatley were able to get. So this is showing the compressibility factor versus density for different numbers, different compositions, amounts of argon versus CO2. And they're showing sort of the effect of the truncation of the series. So you've got 4th order series is dotted points and 5th order is the solid line. And the importance of the 3 body effects are also shown here. And you can see you really can't neglect them if you want to try to get good quantitative results that are competitive with experiment, which of course are shown by the squares. So they also, among other things, reported the Joule-Thomson coefficient for a specific composition, variety of temperatures here, and again, do a pretty nice job relative to experiment. This is subcritical, so it's only going to be able to go up to a certain level of pressure before the virial equation is going to fail. So I really like this paper as much as I've seen of it, and I think it shows the type of thing that I'd really like for us to be able to do with the virial equation state. So just in the last little bit of time, if I do have time to talk a little bit about convergence of the virial equation. This is one of the limitations that we worry about. So, when doing applications with the virial equation. So this is just showing 2 pictures of convergence. So we have CO2, and what's shown here is the estimate of convergence based on the contribution made by the next order term to the series, the virial series. So in this region, this is high temperature, low pressure. This is the Clausius-Clapeyron plot. Again, you can see where the coexistence ending the critical point is. So here the ideal gas law is fine. Here you're okay with 2nd order, 3rd, 4th, 5th. Here you need 6th order virial equation to get within, I think, 1% of convergence. And then up here, you don't have convergence by 6th or 7th order, I should say. So I find this rather interesting that there seems to be a wall here, and there's a thing known as a Whittam line that was discussed at one of the previous seminars, which may have something to do with the limitations on convergence of the virial equation as you get up to here. This is another picture. This is showing our speed of sound calculation, similar type of deal where we've got ideal gas here. The colors aren't the same, but here's second, third, fourth, fifth, sixth order. And what we show on here are we compare it to experiment, and we say, well, where do I have to truncate, or can I truncate the virial equation of state and get a 1% agreement with experiment? And you can see that, those are shown by the numbers here, the order of the virial. And what's really gratifying is that the same point where the virial equation just by itself tells you need, this order to get within 1% of the correct value, comparing to experiment gives us results that are completely consistent with that. Where the virial equation said third order is converged here, comparison to experiment says, yeah, third order is converged there as well. So it's a really nice feature of the equation of state is that it has this diagnostic or self-assessment capability. So ways to improve the convergence. One way that we've looked at are methods, we call approximants, because we started using Pade approximants. And I think this is similar to what Richard Elliott was saying is renormalization. So this just shows you an application to soft spheres. The soft sphere model is shown here. If you do the virial series directly for n equals 4, it's really a very soft sphere model. You can see convergence is just horrible. This is the second order series, third order, fourth, fifth, sixth, and so on. You can see as you add more terms, it converges more and more poorly. And this is compared to the true data that are shown here. So we're able to develop an approximant, and which is basically a ratio of polynomials that's, if you do a series expansion of this ratio of polynomials, you match the coefficients of that expansion with the virial series, and that tells you what coefficients to put in the numerator and denominator of each of these series. And what's interesting with this is that not just any old approximant will work. You have to have an approximant that is consistent with the physical behavior of the model. And you can argue that the compressibility factor will vary with density at high density, precluding any, freezing or anything like that with this behavior and density. So we need to choose an approximant that's going to also have that limiting behavior at high density. And that's what's shown with basically all of these, which are going right through the points now. And that's compared with these other Pade approximants, which don't have that correct limiting behavior, particularly down here. You can see that you can develop approximants that really correct this convergence or enhance the convergence, but you have to be careful in how you set them up. So, another way of extending this was, I've mentioned the critical point is particularly difficult. So we've done a couple things to try to address that using this approximant or resummation idea. So we developed an approximant that is based on what we know as universal behavior of the equation of state as it approaches the critical point on the critical isotherm. So we formed an approximant like this, where A is just a simple polynomial, and we choose the coefficients of this polynomial to match the virial series at low density. And we're able to go from something where we have, I believe this is Leonard-Jones, the virial series are given, again, ideal gas. We've got second order in here somewhere, third. You can see the convergence as you get to the critical point is not so good, but we use this approximant. A 1, 2, 3, 5, and 7 is shown here, which have this form, and you can see we're able to get that pretty well. The square well model, so this was for the critical isotherm. If you go off the critical isotherm, it needs a bit more sophistication. So we use these parametric approximants that are due to Schofield from the 60s, came up with a way of describing approach to criticality from all different directions. And we develop an approximant based on that. And you can see for the square well model that we get really good extension of the performance, going pretty much right through the critical point and agreeing with experimental data. And, basically each of these lines is adding more terms to this approximant. So it's extending the order of the series. So, as you go from here to here to here, it's sort of converging towards something that goes through these points. So this was very gratifying. In the interest of full disclosure, though, it doesn't work super well in all cases. So this is the same thing applied to water. The only thing different between these two graphs is this one. These two slides is this graph. So we did the same thing for water. These are simulation data for water. Just look at the teal line. You can see that this is not going through, these sets of data the way we would like it to, but still, there is some improvement there. And, this is certainly a direction for additional development. Okay, so I'll just very quickly point out something here with the convergence of the virials. I just want to, very interesting result that, if you apply the virial equation to the van der Waals equation of state, it's given by this, this van der Waals loop, and the virial series just goes straight to it. As you add more and more terms, it goes right through it, shows the van der Waals loop exactly as it's drawn here. But it was proved by Mayer in the 40s, and it was resurrected by Michael Ushkatz, who is in Ukraine, I think still okay. I had an email from him after the issues started there, so I hope he's still all right. But he's carried this a lot further and has been really pushing for looking at ways of expanding or extending the convergence of the virial equation beyond condensation. So he presented an exact recursive formulation of the series, which I'm just plopping down here. I'm just showing you that it depends on the number of molecules. It's an n-dependent series. It depends on the temperature shown here. And sorry, the virial coefficients enter in as these betas. So obviously it's not as clean as the virial equation of state, but it's a recursive series and you can implement it on a computer and do calculations. So if you do that for the van der Waals equation, you end up getting, interestingly, and he showed this rigorously, that beyond the spinodal, you get a very flat line, and it becomes flatter and flatter as you increase n that appeared in that equation that I just showed you. So that's, I think a rather remarkable feature of this more rigorous virial equation of state is that it does have the behavior that looks something like condensation, but it appears at the spinodal. So it was something that we did trying to understand this better. We took our Leonard-Jones model, we went to higher order, we computed those higher order coefficients. We tried extrapolating them to even higher orders. And what you find, unlike the Leonard-Jones model, you don't get convergence to a van der Waals loop. Basically, the spinodal doesn't exist. As you add more and more coefficients, the system knows more and more that the liquid is there, and it's not going to, go to a spinodal. It's going to go to something that's trying to condense. So we're able, through this extrapolation, to get to an estimate for the condensation point, which unfortunately is very far off from the true binodal. But it gives an idea of the type of thing that we would like to be able to do. All right, so that's the end of my presentation. I just want to point out that despite 80 years of history, there's a lot that we still don't understand about the behavior of the virial coefficients and the virial equation of state. There's a pretty small community that's working on this in this direction. It appeals to me because it's a rigorous route, feasible route, I think, from ab initio to supercritical fluid properties. Convergence certainly is the primary limitation, and this is exacerbated by association, such as you have in water. I'd like to be able to work around that. But as I said, I think this is a viable route to first principles properties. Certainly is complementary to molecular simulation, particularly for small molecules. So I just want to acknowledge various people who have worked on this particular aspect of the project. Andrew Schultz is just an amazing person. I'm very lucky to be able to work with him. He contributes enormously to everything that I do and everything that I've talked about here. I have valued colleagues at the Rochester Institute of Technology who worked on the convergence issues with me. The PhD students of mine have worked on this particular project, going back to Jayon Singh, are listed here. People at NIST that have encouraged this work, Alan Harvey and Mike Moldover, and I've also worked with Richard Wheatley, who spent a bit of time here in Buffalo working on the extension of his method to multi-body potentials. Okay, so that's all I have to say. I thank you for your attention, and I'd certainly be glad to take any questions if there are any.
Professor Kofke, thank you so much for the presentation. We are now open to questions. If you want to participate, please enable your microphone or write it down in the chat and we will read it. Also, our YouTube viewers can write it down too, of course.
Can I start?
Yeah.
For sure, Professor.
Dave, as far as understood, you can handle electrostatic interactions.
I'm sorry, I didn't, you can what?
As far as I understood, you can handle electrostatic interactions.
Oh, yeah.
Long range interactions.
Right. You don't need,
but-
we don't do any Ewald or any, there's no long range correction. It's basically you sample. There are
Just
complications.
column.
You have dipoles that sort of average to zero, and we have to do special moves that like will flip molecules to try to sort of, capture both arrangements so that you sort of get that, that decay in the interactions, more explicitly. But it's no special measures that are needed to handle electrostatics, other than that, I think.
Interesting. Even for B8 or B7 is the same. What you do with B2
yeah, in
is
principle,
the
it
same
should
as
be.
Yeah.
The molecules will drift away. They can go far apart and sample configurations that are distant from each other. And eventually they come back. And this is all part of the overall, sampling that's done by, the Mayer sampling. It's just, it's an important, to the average, it will go and sample it.
Okay. Carol wants to ask something that I can.
Dave, when you were talking about how much error you get from neglecting this term and that term and this term and that term, and you also talked about errors in experiment. I didn't know how you knew what was absolutely right. What were you measuring everything against in that part?
Yeah, well, that's of course the problem with any type of physical inquiry is you take your evidence as best you can and you try to estimate how wrong you could be. And the people who develop the ab initio potentials, they say we believe the energy is within some amount of the value that we were reporting, and they have various terms that they realize they neglected or they didn't fully account for or whatever, and they think that they contribute no more than this amount. And they include that with the energies that they report, and in the models that they report, they say the error is within 2% of this.
Okay,
and we try to propagate to the properties. It's not a rigorous, straightforward way to do it because the errors are correlated. The systematic error in B2 is going to correlate with the systematic error in B3. But we do the best that we can to try to account for that. So that's how we get our errors. And again, the experimental people, they're of course very astute and they understand, where they're making compromises. And again, they don't get data to infinite number of digits, they get to so many, and they understand that, there are things that are neglecting that contribute, that they're leaving out or not accounting for as well as it could. And they try to present, uncertainties that are, of course, the stochastic uncertainties are pretty easy, you might say, to do. You just repeat the measurement or the experiment over and over and see how much it changes. But of course, systematic errors are more insidious. As you point out, you don't have the true value to compare to. So you try to identify where you could be going wrong. And, you either decide to fix it or you decide that, okay, well, that's there and it's going to cause this much error in my measurement, and they report that with their data.
Okay. Thanks.
Now, Professor Richard Elliott, please.
Hi, Dave. Good to see you.
Hi, Richard. Good to see you.
So you went through the description of how Meyer sampling works, and I thought I heard you say there's some relationship between the way that works and the way MBAR works. And I was wondering.
No. Well, yeah.
Yes, so can you elaborate?
I shouldn't call it MBAR, but it's bar. If I said MBAR, I misspoke, but it's just bar. Bennett's acceptance ratio.
So could you elaborate on that some more and help me understand better?
Sure. So, we always compute the virial coefficients relative to some reference. So typically we'll use hard sphere virial coefficients or some cluster integral for hard spheres. as a known. And just like with free energy calculations, you're computing an integral relative to some other integral, or so a free energy relative to some other free energy. So you can get ratios of free energies, but you have to be careful because these are subject to systematic uncertainties. So the idea is, with this A and B. So the idea is you sample in B and you say, well, how often am I in A? And you would find that it's sort of this fraction that's given by W. And if you just took that as your ratio, well, you never sample over here. So, this part won't, be contributing, and you'll get an error. Your fraction will be off. So we call it overlap sampling, but again, it's more generally known as Bennett's method or Bennett's acceptance ratio. But the idea is you don't just sample B, but you also sample A, and you look at how often that overlaps with B. And you can, it's easy to look at sort of geometrically, sort of the ratio of W to A, and the ratio you can get, correctly, and you can get the ratio of W to B by sampling B, because none of W is outside of B by definition. So those two ratios together will give you the ratio of B to A. And, that's basically the idea of Bennett's method. And we use that. We do a simulation of hard spheres, but we also do the simulation of the target system. And we, measure the fraction of the time that we're inside of W for both simulations. And, that's how we get, the true ratio of the integral we want to the integral that we know. And it's just made a little bit more complicated by the fact that we've got an integrand that can be negative. But it's kind of straightforward to handle that.
Just one point of clarification. You say you're doing two simulations, but they're actually concurrent, right? You're using.
Yeah, I think typically we do them concurrently. It's certainly in the example that I showed you, they were concurrent. The idea, part of the reason is that, there's some tuning that needs to be done. So I'm just drawing this W, but obviously, there's a factor that enters into defining W, and that W depends on the ratio of B to A itself, the thing you're trying to compute. So as you improve your estimate of it, at least you do some preliminary calculations, and you basically get your estimate of the free energy, and that helps you define, what W is. And again, that's how, you do M-bar or whatever, your M-bar, typically you'll just generate all the values and do it afterwards. But here we will, we only have two systems, and, we can run them both and, do the tuning. And then once you've decided, okay, this is it, you then start collecting your data. Well, and, there's actually an optimization as well. The hard sphere calculation typically will converge or give you results to a given precision very quickly. So, you might spend, 99% of the time simulating B and just a little bit of A. And again, Andrew, as works out all the details masterfully to find the best way to implement that. And, so he's, getting the errors from, both sources of simulations, and says, okay, well, we have enough of this, we're going to spend more time on that. And, we'll optimize the allocation of the resource between the two.
So when I said concurrent, what I had in mind was you use the same exact positions over again as part of the calculation as you're doing it on the fly. But it sounds like you're saying, yeah, we do two simulations concurrent. They're on totally different processors. Which way of concurrent are you saying?
I'm saying you've got two independent simulations running at the same time. Whether you have two processors or one, or however you do it on hardware, that's a detail. But they're both running at the same time. Okay,
so you're not using the same coordinates.
No, they're both sampling A and sampling B. As you saw in this cartoon here. This is a reference configuration, and get confused over which one is the this one. Right. So, this is a target configuration, and, that's hard spheres and they always overlap. Whereas, no, sorry, that's the water and they don't always overlap. If I could find, there's one there. So this is water and they don't have to overlap. But if these were hard spheres, like say the red were hard spheres, and again, they're drawn as water, but they're hard spheres, you would never see this in the hard sphere calculation, because the hard spheres basically have a Mayer function as 0 if they aren't overlapping. So they always have to overlap. Whereas, the water, they can go farther away and the Mayer function decays to 0 as you go far away, but it's not straight 0 just as soon as they fail to overlap.
Okay, I think I understand a little better. Thank you.
Okay, good. I'm glad you asked.
So does anyone want to ask another question?
Can I ask a clarification?
For sure, Professor.
Can you hear me?
Yes, I can.
Thank you for a great talk, Professor Kofke, carefully calculating virial coefficients. Especially as an applications man, your calculations on methane and CO2, you went up to 35 megapascal. Is that right?
It sounds right. Yeah. We basically chose conditions that were based on what was reported in that molecular simulation paper.
So, of course, you did not worry about, you already said about condensation.
Right.
You
Yeah.
feel that
these are all supercritical temperatures.
yes, but even at that temperature, say some temperatures like 350 Kelvin, if you go to 70 megapascal, multiple phases may form. It's experimentally, we see this very often.
Yeah, I don't know. Again, I think they're both, CO2 and methane are both supercritical, I believe, at these temperatures. And, unless they're forming a solid or something, I wouldn't expect them to condense, because that's what supercritical means, temperature wise. The temperatures are supercritical. So yeah, definitely as you go higher, it's going to break down. You'll need either more terms in the series or the series won't converge. This is part of what we want to get more understanding of, but there are.
You do not believe it is because of the method. They do not place the molecules close enough.
Oh, no.
Overlapping.
It's nothing wrong with the virial coefficients or, it's just, as you go to higher pressures, the unique interactions that 8 molecules have that are not given by 7 molecules in 1 somehow become relevant to the properties. So you need to get B8 in order to get high pressure properties, high density properties, more to the point. But each coefficient is good. It samples everything that it should, and we are in fact overlapping completely. In some cases, because those are acceptable configurations where they're right on top of each other. So it's not like they're missing that.
The other thing is the theoretical mixing rules for which virial coefficients are exact, right? You don't need a
right.
So can this be valid again, even if you have a 3-body potentials like you're saying, or?
Yeah, so again, the nice thing about, at least at the thermodynamic level, the mixing rules are exact. The virial coefficient for B4 is given in terms of a bunch of other coefficients with mole fractions that have the exact correct dependence. The thing that becomes more complicated, though, is each of those coefficients, as we see, if I can get to the picture to draw, this configuration here. So you've got interactions between CO2 and methane, and in principle you need an interaction. You could have a pair or maybe 3-body interaction that covers two methanes and a CO2, or a methane and one CO2. And these are sort of the mixing rules. And often you'll use, Lorentz-Berthelot or something like that. But I'll just point out that in principle, you can compute those ab initio as well. And that's in fact what Richard Wheatley did in the study that I just pointed to that came out this week. He actually computed 3-body pair and 3-body potentials for the various, 2 CO2s and an argon and 2 argons and a CO2. Those are the other 3-body interactions that are needed other than 3 CO2s and 3 argons in order to, to get all the multi-body interactions. But you can say, okay, I'm going to truncate the potential at 3-body, and you can still get a 5th virial coefficient from that. You're going to be neglecting 4 and 5-body interactions, and that's probably quite reasonable because he actually showed how much the 3-body interactions contributed. The difference between just doing 2 and 3-body interactions, he showed it. Wherever you choose to stop your multi-body potentials, and probably 3-body is as far as we'll typically want to go, but 3-body does matter for the level of accuracy that we'd like to get to. But he did that. He did the calculations for the various sets of molecules and got potentials for them that were not just based on Lorentz-Berthelot or other types of mixing rules like that. They were ab initio as well.
The last clarification, you put out a history of 3-body potentials up to 2000. A long time ago, in the 40s, there was Teller, ETS, the original 3-body potential for hydrogen, tritium, things like that. That type of potential seems to be, is it very different from what you have your Moldova the potential, or it's very similar? Because they vary only in angles.
Yeah, honestly, I'm not that steeped in the various molecular models. These are the ones, these were the state of the art. They are the state of the art right now for helium. And again, this is all helium. These calculations, actually, I don't remember which, the Hurley and Moldover, I guess had a potential from 2000, and, they computed B2 for it. And, this is something that I guess part of the big message from this is, people who are developing potentials, particularly ab initio potentials, I really want to encourage them to compute virial coefficients, because that's a really, great way to validate or invalidate your potential, because you can compare it to experiment. And if you get the temperature dependence virial coefficients right, B2 and particularly B3, that says a lot about the correctness of your model. And I've looked at 1 or 2 sort of ab initio based models, things that aren't based on very much on fitting to experiment, and their virial coefficients are awful. We're quite disappointed. I was planned to compute all these virial coefficients from these models that were out there, and we did the first one, and it just didn't agree with the experiment at all. We're realizing we've got to do this ourselves, perhaps, or find people to work with to do that.
The last comment, we keep using Starling equation, where probably our 5th virial coefficient is sufficient for our natural gas calculations. We are happy with it. What do you think of that? Why Starling equation with only 5 virial coefficient seems to work very well for a complex mixture like natural gas?
You said the Starling equation for natural gas?
Starling, yes.
It's fit
equation of state.
Yeah, I don't know. I'm not familiar with it, so I really can't comment. But if it's fit to experiment,
Starling, I think it's Starling equation.
Yeah. I mean, you're not talking about Carnahan-Starling for a hard sphere. You're talking about methane. Yeah, I'm not familiar with it well enough to be able to give you an intelligent answer about that.
Thank you very much, Professor.
Yeah, thank you for your questions.
Now, Professor Peter Cummings, please.
Hey, Dave. Whoa. Hang on. Mistake here at our end. Okay. Great talk, Dave, as always. Really enjoyed it. I had a couple of questions or comments. I guess one of the comments, and I know you know this, is that the summation of cluster integrals was a really big deal in the ladder statistical mechanics field for a long time. People like Tony Gutman and so on, where they would sum up these diagrammatic expansions to very high levels to try and calculate then the things like the critical exponents of the Ising model and various other lattice models. That whole game kind of got killed by the renormalization group because their interest was only in the critical point, whereas obviously you're interested in much more than just the critical point. But I just wanted to mention that. The other thing I was going to say is there's a cluster integral, and maybe somebody asked this already, I don't know. I couldn't hear everything because I was outside for part of the presentation, but there's also obviously a cluster integral expansion for the pair distribution function that you could perhaps calculate through the Monte Carlo technique. Have you thought about doing that? And
yeah, early on, we haven't done anything with it recently, but we actually looked at trying to get the bridge function, calculations to compute the bridge function, and trying to develop some integral equation approach that sort of took the bridge function and input that, and had some sort of self-consistent way of computing it, but didn't get too far with it. But we did publish a paper, I think, on it, but hadn't looked at it since. So if we were to instead of computing G of R, of course, I think the bridge function is more concise, that contains the same information, and that was the thing we had focused on. But yeah, I haven't done it. That was Sankyu Kwak was the student of mine who worked on that many years ago.
Okay, thanks, Dave.
All right,
Great to see you again.
let me just put a plug in. This Gaussian charge polarizable model, due to Peter and his collaborators, which we did this calculations for. As I said, it's great to be able to compute virial coefficients to validate these models. So this model was developed by Peter and his colleagues, and they didn't use any virial coefficients to fit it. And we went ahead and computed the virial coefficients, and they matched experiment beautifully. So it was a nice validation of that model. I know Peter was excited when we were able to report that.
Yeah, I was very excited, Dave, because it gave me a chance to, it gave me a lot of credibility with Annika Sangers. I talked about this at a Boulder meeting, and talked about how, we use the GCPM model. You then calculate the virial coefficients and reconstructed equations of state. And she was extremely impressed with that. She's never been particularly impressed, I think, with simulation, but she was impressed with this model when it was put within the virial coefficient. Hi, Carol. I see you there. I see Adam behind you too. But anyhow, thanks, Dave. Thanks. I put a thumbs up when you were showing the GCPM model, because I appreciate you pointing out that work. Thanks a lot. Bye, Dave.
Okay.
So does anyone want to ask another question?
I just noticed Andrew Masters was in the chat, but he had to leave. Anyway, he was another person who's done a lot of work with virial coefficients. I said it's a small community, and Andrew Masters is one of the ones who's definitely integral to that. So I didn't notice him in the audience, obviously, but I was happy to see he was here. Again, sorry I wasn't able to communicate with
It's
him.
a small community of 2, 3, 4, 5.
Yeah, right.
So our time is almost over. I want to thank you everyone for this discussion. And once again, thank you, Professor David Kofke, for the presentation.
Yeah, thank you for the invitation. I was really pleased to be able to present this work.
So our seminars are being recorded and posted on YouTube, of course, after the invited lectures agreement. Please check them out on our YouTube channel. And this is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, video editing, certificate writings, and hosting. Thank you all for being here today, and see you next Thursday.